Hello and welcome to this lecture of the course elements of mechanical vibrations. In the previous lecture we discussed undamped vibration absorber, wherein if you tune the natural frequency of the auxiliary system or an attached system to the parent system, tune it to the natural frequency of the parent system, the vibration response of the primary system or a parent system can be brought down to a very low, theoretically 0 value. But there were issues that if the operating conditions fluctuate a lot, then instead of a 0 vibration amplitude, we can actually encounter large amplitudes of vibration, because the two new natural frequencies are not widely separated. Okay. So, there are these issues of an undamped vibration absorber. So, in today's lecture we try to get around with this limitation by introducing a damping element in the absorber design. So, we saw the application of an undamped vibration absorber by tuning its natural frequency with the natural frequency of the parent system. So, we looked at the parent system being in this case an engine which has its own stiffness and mass. In this particular case, it was the torsional stiffness of the shaft and the inertia of the engine. Okay. Then we saw how this auxiliary system was connected to this as an attached additional system having its own stiffness and its own mass, and in this case would be an inertia. So, when the value of the natural frequency of this attached absorber is tuned to the natural frequency of the parent system, we observed that the response of the parent system can be theoretically brought to 0. Now, there is a small catch here, catch in the sense a challenge, that depending upon how much is the mass ratio mu that we use. So, the mass of the absorber upon the mass of the parent system, this mass ratio actually decides how much will be the difference in the two new natural frequency, because once we attach this auxiliary system, two new natural frequencies appear instead of only one corresponding to the primary system, and these two natural frequencies omega n1 and omega n2, they will be separated by some frequency. Now, this gap plays an important role in the practical applicability of this absorber, because if I plot now the response, the original response of the parent system, had it been like this, the moment you have introduced an absorber, it turns out to be this, right, like this. Of course, it will be theoretically 0. But so it would be important to look at this frequency range. If it is too short, which is typically the case, and your operating speed fluctuates, and then what happens is that although you have designed it for this speed, because of the normal speed fluctuations that can happen in practice, you can actually get into large amplitudes because of the closeness to the two new resonances. So, this becomes a challenging part in this case, and to get around it, people have devised a means of reducing such resonant vibrations at the two new resonance positions by suggesting to add a damper or a dashpot, okay, in the absorber system. So, absorber no more now is a simple spring mass system, but a spring mass dashpot system. So you introduce an additional dashpot or a damping element to the absorber system, and the rest of the things are same. Actually, you have a primary system subjected to excitation f cos omega t, where omega is very close to the natural frequency of the parent system. And this system will now be called, instead of an undamped vibration absorber, this is a tuned mass damper. Okay. uh, let us look at how things change now with the introduction of this damper in the system. Okay. uh, Obviously, if you draw the free body diagram and follow the same process as we have been doing for 2 degree of freedom system, you would obviously generate a governing equation of motion wherein the damping element appears. Now this dashpot or a damper, if it is assumed to have a damping coefficient of C1, stiffness of K1 and mass M1, then obviously these are the two governing equations that you can expect. Okay. uh, we have gotten these similar equations for a 2 degree of freedom system except the damping element, but I'm sure with the kind of process that we have learned through application of the Newton's second law, you can get these equations easily. So I'm skipping that part. Let's look at more important fallout of bringing the damper in the scheme of things. Now, because this is a forced vibration case, our assumed solution is obviously going to be harmonic with the excitation frequency. The only thing is, because the damper is now accounted for, we can't we can't ignore the phase, and that gets accounted for or included. Either you can write e to the power j omega t minus phi, or another alternative is to use a complex constant um, for this assumed solution. So what I am going to do is to assume the solution in the form of x bar e to the power j omega t, where x bar is a complex quantity. Okay. So you have x e to the power j phi or minus j phi, which can be clubbed as a complex quantity. Okay. uh, x1 is the response of the absorber, that is now assumed as x1 bar e to the power j omega t. With these assumed solutions, if you substitute back into these equations, we would get an equation like this. Obviously, because when you take the first and second time derivatives, um, you will get complex quantities in these equation, unlike in the undamped case. Okay. So I'm going to now just jump onto these equations without actually fully solving it, because we have a lot more to learn from these equations than just to derive them. I think it is quite a straightforward exercise to substitute these into this equation and simplify it to get this equation. We haven't really reached the final expression for x bar or x1 bar. But when you substitute these assumed solutions in the governing equations of motion, you get these two equations. Now don't get uh, too perturbed by the scale of these equations. Let's focus on the final expression that we get, and develop insights into what do they mean or how to infer from them. Those are more important than the mathematical manipulation or the intermediate steps here. You can leisurely solve this, and I'm sure you will get these equations easily. Now, with these equations, as we have been doing, we have to get an expression for x bar and x1 bar. These are basically going to give you the amplitudes of the response of the primary system and the secondary system. Okay. So how to get x1 bar and x bar, and obviously we will uh, try to normalize those uh, response expressions by using appropriate quantities. So what we do is assume again a static deflection xst of the parent system as f by k, and introduce few more terms like this one. Of course we have discussed in the case of undamped vibration absorber. In this case also the mass ratio is going to be the ratio of absorber mass to the main mass. And then uh, P is the same as the original natural frequency of the main system. The natural frequency separately of the absorber only, that is K1 and M1 defines the natural frequency of the absorber as a single degree of freedom system. And now what we do is, in this case, as we will learn later, that it makes sense to keep P and Q different than equal. Okay, if we do not uh, if we do not separate out P and Q with different numeric values, we may not be able to get the desired output here. So we are going to keep these two natural frequencies different, and let's look into that later. And for that reason, I am going to introduce here a separate variable Rn, which is going to be the natural frequency ratio, the ratio of absorber natural frequency to the main system natural frequency. And we will also introduce a frequency ratio of the forcing frequency and the natural frequency of the parent system, and that is same as R we have seen in the single degree of freedom system. Then we assume that Cc represents the critical damping coefficient of the main system. So Cc is defined with respect to the main system, and the damping ratio here would be the damping coefficient of the absorber here, and normalized with respect to Cc. Okay, so this is only for the sake of mathematical process, and so it is perfectly okay to normalize the actual damping coefficient of the absorber with respect to something related to the parent system parameters. Now with these quantities defined, if you appropriately use them in the equation that we have seen in the previous slide, the expression for the amplitude of the main system normalized with the static deflection turns out to be this. Okay, so again all the intermediate mathematical manipulations are skipped for the sake of brevity. I'm sure you can get this expression without a problem. Okay, so it's just a small simple substitutions and solving it. uh, Again, don't look too much into these equations. We will be definitely discussing what is relevant and what is important from in terms of understanding of what this expression actually mean. This is of course in the numerator and denominator you will see that these are complex quantities. So if you take the absolute value, the response expression turns out to be this, and now it is a function of the mass ratio, frequency, natural frequency ratio, and forcing frequency ratio. Okay, force frequency ratio. So it's basically a function of these three quantities, Rn, Rf, and mu. Okay, you fix one parameter and then vary the other one for different values of zeta. You will get the variation of this response with the forcing frequency ratio. That's precisely what you see here. What is done is a plot is made here for some assumed value of the mass ratio. We can't keep changing each and every parameter here, so we have fixed here the value of the mass ratio to be 0.05, and of course we have also fixed the natural frequency ratio equal to 1, which actually means that if P is equal to Q, what happens. And then when you change the value of RF, the this particular expression is plotted. Okay, as you change the value of RF, how does the non-dimensional response vary? Okay, so this is how the variation look like for one value of the damping ratio. So when you take a very high damping ratio, close to infinity, this is how the response look like. Now, if you really see this system, okay, the parent system and the vibration absorber with the damper, what is zeta equal to infinity? What would it actually mean? That the dashpot fluid is so viscous, it just does not allow any relative motion. Okay, it's so viscous, in an extreme condition it will simply lock. The moment it simply locks, the two masses becomes one. There is no relative motion. And what you see is again another single degree of freedom system with a different value of mass and the same parent system stiffness, right? So this graph is actually representing what physically we can expect. Now, if I change it and of course take a different value of damping, so I go and take the another extreme value of the damping ratio, that is 0, you expect two different systems vibrating together, and so you expect two natural frequencies, and that's what you have, one resonance here and another resonance here, okay, for a different RF value, okay, instead of one for a damping ratio infinity. So by changing the value of zeta, the character of the response obviously is changing as expected. It is plotted for the same parameters as we have defined earlier. Now if I take an intermediate value of zeta, not towards one extreme of 0 or at the other extreme of infinity, 0.05 I have taken it here, right? So what happens? The value of zeta, a small value of zeta, obviously from mathematically infinite amplitude, it reduces the amplitude at these two resonances. So you have a more appropriate response which is not reaching infinity at any RF value. So as expected, a dashpot or a damper, introduction of the damping element, will contain the vibration response at resonances, which is what is happening here. Now the problem is we have drummed up so much about use of this vibration absorber for containing vibrations or reducing vibrations of the parent system to 0. So this was the ideal situation, but that ideal situation created a problem for us, that there are new two resonances and any deviation from this operating condition would take us closer to the large amplitude cases, and therefore we introduce a damping. Now what a damping has done, it a small 0.5% damping has increased this 0 response to a higher value, okay, but it allows you to operate over a wider frequency range without significantly increasing the amplitude. Okay, you have a reasonably wide range of operation. For example, if I operate it somewhere here, the introduction of damping is now so let me erase some part of it. So if I consider the operation at this speed away from the desired operating speed, the damping is definitely causing the amplitude to be this small, okay, whereas had it been without damper it would have reached to this value. If I operate it close to 0.9, it will limit it to this, but you can expect much larger amplitudes without damping. But instead of 0 response, you have some non-zero response. Now your job as a vibration specialist could be to ensure that the response is not zero. You know, it's an impractical desire to have absolutely zero response. If you design it based on some standards, the standard says that as long as your vibrations are within this limit, the design is fine. For example, API standards for the design of pumps tells you that your quality factor, you know, should be less than 8 or so. Preferably, if it is close to 5, perfect. Okay, so in general, if you design it to lie between 3 to 8 or maybe 6 or 7, in this range, this quality factor is perfectly okay. Okay, the moment this quality factor goes beyond 8 or 10, your design is not really good. You have to rework on your design. Now look at what is happening here. What is your quality factor here? It's close to 8 or 10, right? And at what is happening at your most likely operating speed, it is close to 4. That means your design is okay. What will happen if you go away from this? Maybe this 4 will become 5 or 6 or what. That's okay, right? So in that sense, even if you are not actually getting zero response at your operating speed, because it is not such a big hassle to have non-zero but limited vibration response, I think it is a good job done. Okay, so in that sense, tuned mass damper is going to be a nice design to be implemented for containing vibrations. The only issue here is that for different levels of damping, you be aware that sometimes this graph can really become steep, and maybe this will become like that. So the question here is, how do I optimize uh, the response, or how do I optimize the parameters of this vibratory system, like the stiffness, the mass, and the damping coefficient of the absorber, so that I get a perfect or a desired response from the damper. So the expected response or a desired response could be this. If you really look at how a larger damping is going to give me, is that a larger damping is going to increase the amplitude to this level, and as I keep on reducing the damping ratio, uh, the extreme, as I said, is zeta equal to 0. It gives you these two new resonances. But if I take a smaller value, let's say 0.005, it gives you the response something like that. And if I ensure that the damping ratio is properly optimized, I get the response which is not showing stronger peaks but are reasonably well contained. Okay, now if I go back to this previous case, what is interesting to note here is that if I try to reduce this amplitude goes up. So it's like, you know, you cannot have an optimized solution here. So the basic philosophy of the design of this tuned mass damper is twofold. So there are two steps here. One is that we ensure, suppose I call this point as point number P and this point as point number Q. The first objective will be to ensure that the amplitudes at these 2 points P and Q are equal. Now why is that so? What is so special about these 2 points? If you notice in this graph, if you notice clearly in this graph, these are the points through which all the curves irrespective of the damping value pass. Okay, so what it actually means, that if I bring them their amplitudes at these 2 points equal, so all the graphs will pass through these points. So it might happen that this amplitude will go up, and but this will come down, and I will have a same amplitudes at these two points of interest. Okay, but that is not enough. Just to bring these amplitudes equal is not enough. For example, in this case, if you see this green colored case, that even if I bring these amplitudes equal, the graphs will pass through this point, but then they will show up with larger amplitude at some other value of RF. Okay, so the way to bring these amplitude at these points equal is by proper tuning of this Rn value, the ratio of the natural frequency of the absorber and the parent system natural frequency. You will soon understand how we can do that. But the first step of designing this tune mass damper is to first ensure the tuning, in the sense that these amplitudes are identical, and more importantly later ensuring that you choose an appropriate damping parameter, damping factor, so that the curve passes with zero slope at these points. The moment you ensure that the curve pass with zero slope at these 2 points, both these points, that will ensure that the graph does not shoot up on either side of that point, and then the graph will have a flatter, this kind of a response. And if you ensure that the largest response amplitude is within the desired limit which you can set, then you don't really worry about the varying speed conditions. Okay, and then the fact that for an undamped vibration absorber, the problem always is large amplitudes at the nearby resonances, and limiting a very strict regime of operating condition that gets relaxed, and then you don't have to worry about resonances throughout the operating speed range. So this is the basic philosophy of the tune mass damper design. First is you somehow get to have these two response amplitudes to be identical, and then optimize the damping factor so that the graphs pass through zero slope through these points, and that will ensure that the response is contained and limited at all frequency values. Okay, so this is basic philosophy. Okay, how do we achieve that? How do we achieve that? So if I have shown you here, if the mass ratio was selected equal to 0.05, for this mass ratio, if I don't tune your absorber, then the response that you are going to get is this kind of a response, where this amplitude will be different than this amplitude. Okay, this is what happens when Rn is not tuned. So by forcing these two amplitudes to be same, you basically figure out what value of Rn that I will be choosing, and the next graph essentially tells you that if you choose this Rn value properly, right, in this case it was chosen equal to this value. How we have done, how we have chosen this is something which is going to come up shortly. But the point I am trying to stress here is that if you optimize the absorber in terms of its frequency ratio, natural frequency ratio, these amplitudes will turn out to be identical. Okay, that is the first step, as I have told you in the previous slide. This is your first step to make sure that this and this amplitude is identical, and that happens by tuning the natural frequency ratio. Once you have done that, then you have to tune the damping coefficient or a damping ratio of the absorber. So that basically is the second step. So of all the various damping factor graphs that you see here, they do pass through this point, but they show up with a larger amplitude here or larger amplitude here. But this graph, if you look, focus on, that graph has an optimized damping factor which generates a zero slope at these 2 points, and then irrespective of where you operate throughout this frequency range, you do not get to see a large amplitude rise. Okay, so that is basically the philosophy of design of a tuned mass damper, and such dampers are obviously used in practice in automotive industry and in civil structures. We have seen them, and our job now is to really look at how to find these optimal parameters. Now, just to give you an example, that instead of a mass ratio of 0.05, if I choose a slightly different mass ratio, not slightly, of course, much larger, mu equal to 0.2, look at how low the amplitude can come down. You see this, this is typically maybe about close to 3 units. Okay, the amplitude ratio, how much was it here? Close to 6. Okay, so by choosing the mass ratio, you decide how much maximum amplitude that you can allow. Okay, accordingly you can choose the value of mu, and once that value of mu is fixed, you can decide how much should be Rn, or Rn gets decided based on that mu, and then zeta has to be decided, and then you will get the response very much within the limits. That is basically the whole approach that we are going to follow. And obviously, when mu was chosen to be 0.2, the natural frequency ratio, instead of 0.96 or something, it will turn out to be 0.83. So this natural frequency ratio, instead of oh sorry, not this one, your absorber natural frequency Q, absorber natural frequency Q should be 0.83 times P. So if your natural frequency of a parent system is known, you can immediately choose the appropriate stiffness and mass values to for complying this equation, and therefore you can see that the zero response will be much more shifted on this side based on the mu value. But once the mu is decided, Rn gets decided based on that, and of course damping factor will have to be evaluated. Now we have always all the time talking about an appropriate value of mu, and then Rn gets decided, Z gets decided, but where are they coming from? How are we calculating these values? This is something which we are going to discuss based on the initial expressions that we have got. Okay, how do we select or design the parameters? So this is the equation that we have already obtained in the initial solution process. Now we will start from here and gradually look at the expressions for the value of natural frequency ratio and the optimum damping. As we discussed, this and these 2 points are critical point, these are important point for us. What we should be looking at is how to somehow get the amplitudes of these 2 points to be identical. That's our first target. So we define these as point P and point Q, and it is possible for me to find the response for zeta equal to infinity from this expression. How do I get that expression? Divide the numerator and denominator with zeta, okay, and set this zeta equal to infinity. You can find this from this equation. It's easy to get this equation by that manipulation. Okay, so this expression tells you what is the amplitude ratio when zeta is infinite. Of course it is a function of RF and mu. Now you would wonder why this expression is important for us. Now instead of all the time using this very complex long equation, because of the fact that this point pertains to all the graphs in the sense it is applicable for any zeta value. Okay, so it will apply for zeta equal to infinity. That means if I want to find out the amplitude of the response at point P, and P I mean for the given value of RF here, I can use this expression. Okay. So if I substitute for the RF for this point and use this equation, I will get x upon xst corresponding to P and corresponding to Q. For Q, of course, I will have to use this RF value. So this is one equation which we are going to use for our analysis. Okay. Then x over xst, that is the amplitude ratio, is going to be independent of this damping ratio when this equation is satisfied. Now again, this might be little mind boggling for you. Why are we doing this? You will realize that very quickly. It's a simple mathematical jugglery here to show that if this expression is equal to plus or minus of this expression, and if you substitute back into this equation, you will find that zeta goes out of the scene. The equation will be devoid of, or zeta will disappear. It's quite possible to show that. Okay, we will not get into that. Okay, trust me that this is, when this is valid, you will find that x over xst expression zeta disappears from it, which actually means that if this condition is satisfied, it pertains to this point and this point. Does it not mean? If this is satisfied, and if you substitute this here, this expression will be independent of zeta, and that means we are referring to the positions of point P and Q. Now you have two possibilities, plus and minus. Okay, if you use positive sign, you will find some value of RF. I am leaving it to you to try and figure it out yourself what that point will be. Okay, but if you use negative sign, you get this expression, and it's quadratic in RF square. You will get two values of RF, and which are expectedly for the 2 points P and Q, right? One of these two sign gives you one value of RF, and you find out why, which one, but the other sign gives you a quadratic here, and that if you solve, you will get two possible RF values, RF1 and RF2. Is that clear to you? So what we have done is that we found that if this is satisfied, the expression x over xst is independent of zeta, and that is basically referring to these 2 points where the amplitudes are independent of zeta, whether zeta is equal to 0 here or infinity or some 0.005 value here. All of them will pass through these points. So if this is satisfied, it is actually referring to the location of P and Q in the RF x-axis. If I simplify this or use an appropriate sign on the right hand side, I get this quadratic, which is going to give me the solution of which will give me two possible RF values. So RF1 for P and RF2 for Q. Okay, so I will get precise location where P and Q on the x-axis are located, right? So this is one expression which is of importance to us. Now I can add RF1 and RF2. So the two values of, or two expressions of RF1 as well as RF2, which I will get by solving this equation. If I add the expressions for RF1 and RF2, I get this expression. Now hang on for a while. You don't get bogged down by the length of the equation. We will have enough time to understand the implication of these equations. Okay. Well, after this, our job is to set xp equal to xq, right? What is the expression for the response at P and Q? Can I use this expression? Because this expression is for zeta equal to infinity. We have still not decided which value of zeta we are going to use, but it is very clear that if this value of zeta equal to infinity expression uh, will also belong to this point, because the curve of zeta equal to infinity passes through both p and q, right? So what I am going to do is I am going to use this expression, okay? And so what is happening is that uh, for x equal to x of the value of response x at point p, I can use this expression, and also for the response at q I use the same expression. The only thing is their values will have rf1. So in the expression for rf, I'm going to use rf1 as the frequency ratio, and in the second part, that is for q, I'm going to use rf2 as the frequency ratio. Okay, so basically I'm using this expression to represent the response at point p and separately response at point q. Why are you putting a negative sign here? Think about it. Hmm? The reason for putting a negative sign there is, if you remember x over xst for a single degree of freedom system, what is that expression? Undamped case, right? This expression for r less than 1 will be positive, and for r greater than 1 will be negative. So this one and this one will have two different signs. One will be positive, the other one will be negative. So when you compare these two expressions for the response, this one for the response at point P and this one for response at point Q, okay, of course using frequency ratio RF2 for this point and frequency ratio RF1 for this particular point. Okay, now if you equate these two expressions for the two responses at point P and Q, and solve this, cross multiply and solve, you get summation of the square of RF1 and RF2 to be given by this expression. Okay, so we have taken two routes. One route was to get this equation, because when this left hand side is equal to this right hand side, this particular expression is independent of zeta, which actually refers to these 2 points, and then we got this rf1 and rf2, or the summation of squared values of rf1 and rf2 to be given by this expression. That was one route. The second one was by looking at the amplitude ratio for zeta equal to infinity, and because all graphs passes through these 2 points, at zeta equal to infinity graph will also pass through these points. So if I ensure that this RF is equal to that for point P and point Q, I can use this expression. And when I compared and equated these two expression, because that is my condition for an appropriate design of the tune mass damper, that I must force the two amplitudes to be equal. If I allow them to be different, you will be having xq very little, but then xp will shoot up. Okay, so instead let us have both of them equal, and whatever is the amplitude, that gets decided based on the value of the mass ratio mu. Okay, so by using this condition and equating them, I have now the second of the two equations. So this is the second equation, this is the first equation. Both of them are referring to the same frequency ratio, forced frequency ratio, RF1 and RF2. If I equate these two now, I get an expression for Rn. What is Rn? It is the natural frequency ratio. What you have got that as a function of only one parameter, that is mass ratio. Okay, so through this whole process, what we have been able to do is, given a certain value of mass ratio mu, I can now fix the natural frequency ratio. Okay, or I have a direct value of Rn, which is the natural frequency ratio. It is a function of the mass ratio. What if I choose this natural frequency ratio? What is definitely guaranteed is that you will have same amplitude at points P and Q. Okay, if you have seen all the previous graphs, please look at the previous slides. If you do not tune this Rn properly, you will have different values of P and Q, and then at some frequency you may have a lower amplitude, but at other frequency the amplitude shoots up. You don't want that. So by forcing xp equal to xq, you are able to generate a relationship for Rn based on a given or a chosen mass ratio mu. Okay, but the job is just half done. Why? Even if P and Q are made equal, some damping ratio would still take these amplitudes at a higher level. Okay, just having these P and Q amplitudes equal is not enough. So you have to now tune the damping. Choose a damping so that the graphs pass through these points with zero slope. That will ensure that they do not increase at other RF values. So if you solve this RF, but now in the expression what I'm going to use is that I'm going to now substitute for a tuned um, natural frequency ratio. So now Rn is not arbitrary Rn. Rn is being forced to have a value of 1 over 1 plus mu. Okay, because we have decided that we will have the xp and xq to be identical. So Rn is going to have a value of 1 over 1 plus mu. If you substitute Rn for this expression in the equation, which is this, you get the expression for the force frequency ratio RF to have these two possible values. Now make a note here that by replacing Rn in terms of mu, everything will be now in terms of the mass ratio mu. So two possible values of RF are obtained here, which are dependent on the mass ratio and pertains to a damper which is a tuned damper. Okay, all right. So that basically gives you these two new forced frequency ratio, but will be basically pertaining to the case where xp is equal to xq. Okay, now if you choose the value of natural frequency ratio tuned following this expression and use it in the expression for the force frequency ratio obtained from this expression, then you will have an expression for the force frequencies which are corresponding to these 2 points xp and xq. And then what we can actually do is to use the expression for the response corresponding to this zeta equal to infinity. Now the graph of the response for infinite damping ratio also pass through P and Q, and so if you substitute for RF star 1 and RF star 2, from which you can obtain from this expression, you can get the amplitude ratios for P and Q. Now this amplitude ratio P and Q would obviously be equal, and which relates to this graph. So here what the graph shows is that if you choose this particular natural frequency ratio for, let's say, a value of mu equal to 0.05, the Rn turns out to be 0.952, and if you choose this value of Rn equal to 0.952, then the graphs would look like this. That means the amplitude at point P and Q will be identical, as you notice here, and the expression for the force frequencies xp star, sorry, RF P star and RF Q star, they will be obtained using this particular expression. Okay, so it so means that once the tuning is done, by way of choosing natural frequency ratios, the amplitudes gets fixed to an expression given by this. That means it again is dependent only on the mass ratio, as we have found from this expression. Uh, and then if you are not tuning your damping ratio, okay, so if xp and xq are obtained using this expression, you cannot expect everything to be fine, because as you notice here, the graphs for different damping ratios, for example, this graph is for 0.01 damping ratio, that although has the same values at p and q, but will have a larger amplitude at some other frequency ratio. So that is definitely not a good damping ratio for appropriate tuning or appropriate design. If you choose a slightly different damping ratio like 0.005, the graph has very low level of amplitudes between p and q, but beyond q the amplitude again shoots up a bit. And so that means we need to ensure, as we have discussed, the basic design process is not only have xp is equal to xq, but also appropriate damping ratio to be chosen. Now if you somehow choose the damping ratio so that these graphs pass through these 2 points with zero slope, then neither on this side nor on this side the graphs would exceed the value of xp star and xq star, that is this particular value. And that you can do um, by first differentiating this expression, differentiating it with respect to rf. And in that expression, if you choose rf equal to rf1 star or rf2 star, which means that the graph um, should have a zero slope there, which means that the differentiated quantity with substitution of rf1 star will mean that we are looking at the slope to be zero at this point. If you equate that expression to zero, you know how you obviously agree that it will lead us to the optimized value of zeta, which will ensure zero slope while passing through p star. On similar lines, if you use this drf of x bar over xst, this expression, and in this expression substitute for rf equal to rf1 star and then equate it to 0, this solution will give you zeta optimized at point p. Okay, and instead of rf1 star, if you use rf2 star, which you will get from this expression, then you will get the solution will lead you to zeta optimized but at point q. Now usually it is seen that if you do this way, and this xp and xq or p star and q star are here, okay, having the equal amplitude, if you optimize it for p, it will not be optimized for q, but then it will not peak to a larger value. If you optimize the damping ratio at q, it will definitely have a zero slope here, but maybe slight increase will happen at point p star. So therefore what is done is you find out uh, what is zeta p star and zeta q star by the expressions that you can derive based on the process that we just discussed, and you can average out the xp and xq, sorry, zeta p and zeta q. So it is possible to show that the optimized value or expression for zeta is given by this expression. The moment you use an optimized damping ratio based on this expression, you will have zero slope at both, um, more or less zero slope at both p star and q star, and then you will have a much lower vibration response at a wide operating speed range, and you don't really have to worry about the kind of resonances which are generated by attaching the absorber. So in nutshell, what we have seen is that, leaving aside all these derivations, there are these two or three important expressions that basically are necessary for the appropriate design. First is tuning the absorber so that the natural frequency ratio is given by this expression. Now there are two ways. One is, you fix up the value of mu and then find out this ratio and figure out what maximum amplitude gets reached. Alternatively, you decide how much are you going to allow this value, large amplitude, at P or Q. Once this gets finalized, so for example, I may limit the amplitude ratio xp, sorry, or x bar by xst to be 5, okay, and then if I use that 5 here, I can get an expression or value of mu based on that value, and then this mu value can be substituted into the expression for Rn, and that gives me the relative values of P and Q, because we know that Q upon P is your Rn. And then you can design, either choose K1 or choose M1, and based on that you can design your absorber. And we know that it is not sufficient to do that way, but to also ensure an appropriate damping ratio so that the graphs passes through zero slope, passes through P and Q with zero slope. And because we have already decided on the value of mu, so it's just a simple straightforward substitution of mu into the expression of damping ratio to get an appropriate value of optimized damping. Once all of these are finalized, then you have a design at your hand, right? So the expressions are little lengthier than what we discussed till now, but if you follow through this discussion, it's quite interesting to see how these tune mass dampers are actually designed. It would be nice now to look into um, an example of a practical system. So for example, the reciprocating compressors case here. So this is a compressor that is being connected to a flywheel like here, okay, and through a shafting. This compressor is having a solid steel shaft of given diameter here, generates excessive torsional vibrations in this operating speed range. The mass moment of inertia of the compressor is given 1.5 kg square meter, and that is basically the value of I. So I'm writing this as IC value. The flywheel is large enough so that we can treat it to be fixed, so we can fix this, and then it becomes a torsional vibratory system. This is becoming your primary vibratory system, okay. So that's our primary or main system. So it has its own stiffness based on the diameter, and the inertia is given. The torsional natural frequency of the system turns out to be 5.1 hertz. So that basically means that your P is equal to 5.1 hertz. You can convert that into radians per second. Ensure that all the units are appropriately taken. Okay. Design an optimum auxiliary mass damper so that the maximum amplitude of vibration is limited to 2.5 degrees. Okay, so now here I am restricting the largest amplitude, torsional vibration amplitude, theta st, to be 2.5 degrees. Oh, sorry, theta bar is 2.5 degree, and divided by what? Theta st. Now that you can get, because it says that the gas torque is having a primary component of 20 Newton meter. Mind you, it is a reciprocating compressor, so you will have primary and secondary torque. And more importantly, it is for the sake of simple calculations, it is declared that it is independent of speed of rotation. So you don't worry about the variation in the primary component over a speed range. So assuming that to be the case, we know theta st, that is the static twist in the shaft. It's going to be what? T by kt. Okay. Now, so 2.5 divided by primary component, which is T, is 20 Newton meters. So, sorry, let me separately write it here. Theta st. So, theta st, if it is in the denominator here, this theta st is going to be 20 Newton meter divided by kt. Now, the question is, how do I know this kt? I already have p of, declared. The given value of the p is 5.1 into 2 pi, which is equal to what? Square root of kt over ic. The parent system's natural frequency is k over m. In this case, in a torsional vibratory system, it is the torsional stiffness of the shaft, okay, divided by the inertia of the disc here, compressor. So I know ic value, it is given. So if I substitute, I will get the value of kt. If I use this kt into this expression, I know what is theta st, right? So that's how it is, like theta bar over theta static is equal to 2.5 into divided by this kt, okay, t over kt, right? So 20, and this is divided by this kt is going to be 5.1 into 2 pi, this is whole square, multiplied by ic, which is 1.5. I hope I have not made any mistake here. Okay, so this is going to be this ratio. Now, if you are supposed to design an optimum auxiliary mass damper, you know what is the expression for this? You remember xp star upon xst was given by this expression. Look at this expression, right? A square root of 2 plus mu upon mu. Is it not? Now this is already given, this is already known from this. Instead of x, we are going to use theta, that's the torsional vibration. So because the left hand side is known from this, right? So you will get to know what is the value of mu from here, right? And what will that suffice? Now from this, because it has to be a tuned mass damper, we know that this has to be 1 upon 1 plus mu, right? The moment you know this mu value, you know Rn, which is what? Q over P. This value is known. So Q is known because P is given 5.1 into 2 pi, okay, into this expression. So you know Q. And what is Q? Square root of Ka absorber by Ia absorber. Okay. Now what? Zeta. What about zeta? What value of zeta will you choose? We also know that the optimum value of zeta is how much? 3 by 8. Isn't it? That's the expression we have. Okay, so mu is known, so zeta optimum will be known. Okay, and yes, what will you use now? Anything else? You have already estimated the value of mu, right? Which is what? IA over IC. Okay, so this is your absorber inertia, and this is the inertia of the compressor. Okay, this is the compressor, and now the design of the absorber means what is the value of this torsional stiffness of the shaft connecting the absorber inertia, and what is the absorber inertia itself, isn't it? Now mu is equal to IA over IC. IC is already known, so you can find out from this the expression or the value of IA. Is it not? Hmm? Yeah. How will you find Ka? Once IA is known, you can find out Ka as well. Okay. And from the earliest of all our expressions, you can also find out what is x1 bar. Okay, which is the amplitude of the auxiliary mass. And why is that important? That you might have been able to lower down the amplitudes of your parent system, the compressor, but it would be necessary also to know what is the amplitude of the absorber. Okay, well, how much is the twist in the absorber inertia, and that will help you find out what is the stress which is generated in the absorber connecting shaft, and that amplitude should not be large. Of course, it will not be too large as compared to when it will be when it is not it is not properly designed. Okay, so this is how we implement or use what we learned about the design of the vibration tune mass damper. um, how the tune mass damper is properly designed, and if it is properly designed, then you will have much lower vibratory amplitudes. Much lower vibratory amplitudes means the stresses in the various elements, flexing elements, will be limited, and you will have a robust design. The design will not fail in operation. That's how the design is all about. Okay, let's take a look at another kind of a damper, Houde damper for this automobile engines, where the crankshaft's torsional uh, deflections, vibratory motion is damped, substantially by use of these kind of dampers. Okay, so the damper actually is an inertia in the form of a disc which is floating in an annular space, maybe of a pulley which is there to drive the accessories. Okay, so this is your end of the crankshaft, and on the end disc or a pulley you have an annular space, and in that annular space silicone fluid is filled, and then also you will find a disc which is floating in that space. Okay, separated from this pulley through the viscous fluid here. Okay, and it is freely floating. So if you now try to look at this system, that system is actually maybe a torsional stiffness of the shaft here, and followed by an inertia which is that of the engine. So engine inertia can be this, or you can also have a pulley here. So this inertia is that of the pulley, if you want to write this as IP. And then you have another inertia, that is the absorber inertia. So that absorber inertia is suppose denoted as IA. The interesting part of this connection here is that it is not connected by a spring and a dashpot, but just a dashpot. Okay, assuming that the fluid does not provide any significant stiffness, but quite a substantial amount of damping. So the connection is through a dashpot, and this is a novel design, um, came almost like a century back, uh, and then started getting used extensively in automotive engines. So if you really look at this closely and compare it with the kind of connection of the absorber that we had in the previous case, where a spring and a dashpot with this inertia is your absorber system. Now you have only the dashpot. Now the first casualty here is your Q. What is Q? There is no spring there, okay, and Rn being Q over P is going to be 0, okay. So in this case Rn is 0, and then you can start working out on all the expressions that we derived for the usual case. So we will not get into all the steps again, except for the fact that if you substitute all of these quantities appropriately, this is what the response plot of theta will look like, the torsional deflection of the main system. Obviously we would be interested in reducing the torsional oscillations of the pulley, because the belt is running over it. We do not want large torsional displacements there. So what happens if the zeta is very large? So this is like representing an infinite value. You expect this curve, okay, and when there is no damping, so very low level of damping, even for a damping of 0.01, this is what the curve looks like. Both of these curves are almost identical in its behavior, okay. So why do you get, it would be interesting to understand why do you get lower resonance frequency for zeta equal to infinity compared to when zeta is equal to 0. We partly discussed this in the earlier discussion, okay. Zeta infinity means these two are actually getting clubbed together. The two masses will club together, and then you will have a single degree of freedom system, and the mass being heavier or larger, your frequency will drop, it will be lower. With zero damping, it is sort of not being there at all, and then you have a higher frequency over there. Okay, what is the response for an intermediate damping case? 0.1, this is what you get, okay. And the way we saw in the previous case, we have a point, interesting value of the force frequency ratio, where all the graphs irrespective of the damping passes. So this again, the derivations are quite similar. We will not get into those derivations because we have already discussed a lot on that. So it is possible to show that the value of Rf, the force frequency ratio, for this point is going to be given by this expression which you see. And so if we manage now to adjust this damping ratio so that it passes through this point with zero slope, then you would have no very large level of vibration, torsional vibration. So what is the objective now is to figure out what is this zeta optimum, so that the graph of the response passes through this point with zero slope, okay. So again, similar approach as we have discussed in the earlier part can be followed, and it is possible to show that the response turns out to be this if is this at this particular RF value, and the damping, if it is adjusted to this expression given by this expression, then this remains the maximum response, okay. The response at RF star, this is going to be your RF star, is given by this expression, but if you do not choose appropriate damping, the response as you see here can go to a higher level at some other RF value, or you may have something like that, okay. So to avoid this, if you choose an optimum damping given by this expression, again this expression can be obtained by again taking a derivative of the response and then setting that to 0 for RF equal to RF star. This is all what we have discussed. So this is the way the design of an Houde damper for automotive engines uh, can be made. Okay, so this is these are all the relevant expressions related to this damper, very commonly used and very effective to contain large torsional oscillations. All right, having done this, we could discuss an example that I think will be given in an assignment. And so as an example on this damper can be tried out yourself, because all the expressions are all pretty straightforward. So the question will be how to choose mu, but you can actually decide how much allowable torsional stiffness that the shaft can bear, or what you can allow. So again, from the stress consideration, theta can be limited, and with that limiting value of theta, mu gets decided. Once mu get decided, then you have only this expression to find out and figure out what should be the effective damping coefficient provided by this fluid in that cavity. Okay, so again, if you want to know that how this zeta is calculated, there are expressions for which the design parameters will be the clearance in that space, the viscosity of the fluid, and so on. Okay, and the dimensions of the disc. So those expressions can be used to adjust the design parameters like the diameter, the clearance, so that you get an effective zeta equal to what you have calculated from this particular expression. So of course, once you use optimum zeta, this is how the response would look like, and that pretty much gives you an idea that if you put a cap on what maximum torsional deflection that you are allowing, based on that mu gets finalized and the zeta can be finalized, so that you get the curve like this. And now you can see that at no other point the amplitudes are beyond this particular limit, right? So that's the way to design the damper. Okay, to summarize this lecture, we explored today through a detailed discussion as to how the major lacuna of an undamped vibration absorber can be addressed by suitably introducing a dashpot or a damping element in the absorber configuration, and then the attached system is then called as a tuned mass damper, where the mass damper is tuned at the frequency which is not necessarily the same as the parent natural frequency. In fact, it will be slightly different, but also you suitably adjust the damping in the absorber, so that over a very wide range of operating frequencies, the large amplitudes of vibration can be contained. And these two lectures basically highlight a possible vibration control measure that you can consider if the system is vibrating with resonant vibration amplitudes. We then had a brief discussion on automotive Houde damper, where the torsional absorber is basically floated in a cavity containing a viscous fluid, and that damper then can be designed to suitably control the torsional vibrations of the automotive rotating shafts. So, based on today's lecture, these are the couple of review questions for you. And these are the answers, you can check.